Hey everybody, welcome to AlgoExpert. In this video, we're going to cover the question of all kinds of node depths. If this question sounds familiar, it's because it's very similar to another question that we've got right here on AlgoExpert called node depths, except this one is much more difficult. Basically, we're given a binary tree, and we're reminded of what the depth of a node is in a binary tree. The depth of a node is its distance to the root node in the binary tree. So for example, the depth of the node with value 8 in this entire binary tree here is 3, because it's 3 edges away from the root node. And we have to write a function that is going to sum the depths of all the nodes in all of the subtrees of the input binary tree. The best way to understand what exactly this question is asking us is to just go through an example. So here for this particular binary tree, the answer would be 26. And the way that we get 26 is by looking at the sum of the node depths in each subtree in this input binary tree. So the subtree that's rooted at 4 here has a sum of node depths of 2. So I'll write it down next to it here, 2. And the reason it's 2 is because this node, the node with value 8, has a depth of 1 in the binary tree rooted at 4. And this node, the node with value 9, has a depth of 1 in the tree rooted at 4. Then the tree rooted at 3 here also has a sum of node depths of 2, because 6 and 7 both have a depth of 1 in the tree rooted at 3. Then the tree rooted at 2 here has, let's count them, it has the node with value 5 that's got a depth of 1. It's got the node with value 4 that also has a depth of 1, so that's 2 if you sum them up. And then it's got the nodes with values 8 and 9 that have depths of 1, 2, 1, 2. So you sum 2 plus 2 plus 1 plus 1, and you get 6 here. And then finally, the input binary tree, the tree that's rooted at 1 here, if you grab all of the depths of its nodes and sum them up, you get 16. And we can count them really quickly. 8 and 9 are both 1, 2, 3 away from the root node. So they both have a depth of 3. So that's going to be 6. Then 4, 5, 6, and 7 all have a depth of 1, 2, right? 1, 2, 1, 2, 1, 2. So 2 times 4, that's 8. 8 plus 6 is 14. And then 2 and 3 both have a depth of 1. So 14 plus 1 equals 16. And I guess I should also mention that the leaf nodes in our input binary tree, they have node depths or sums of node depths of 0 because they don't have any child nodes, so there are no node depths in the trees rooted at these nodes. And so if you sum up all of these numbers here, you get 26. Now, the other question that we have on AlgoExpert deals with these node depths was much easier because all that it asked us to do was to return this value, this 16 here. It only wanted us to calculate the sum of node depths in the main input binary tree. The input binary tree rooted at the node that we were given. For this question, not only do we want this value, the value from the easier question, but we also want the equivalent value for all of the subtrees in the input binary tree. And we have to return the sum of all of these values. So as you can imagine, there are a lot of node depths to calculate, hence the name all kinds of node depths. Now here, I will say that I'm going to assume that you've already done that easier question, because I'm going to take some of the stuff that we cover in that question kind of for granted here, or at least I'll gloss over it very quickly. If you haven't done that question and you feel very uncomfortable with this question, you don't feel comfortable with how to get this 16, for example, here, I would encourage you to pause this video and go do that question first and then come back. But either way, I'll very quickly remind ourselves of how we can get this 16, what the solution to that easier question was. To sum up all of the node depths in a single binary tree, not the subtrees, right? Just a single binary tree. We could write a very simple recursive method in just a couple of lines of code that basically adds up the depth of a given node, and we start at the root node with a depth of 0, because the root node has a depth of 0 in the tree rooted at the root node. And then we also add up recursive calls to the children nodes of the root node and then of every node thereafter. And whenever we make these recursive calls, we add 1 to the depth of the nodes. So if I erase all of these values for now, let's just erase them. We might re-add them a little bit later if we need them. But the way that this method to get that 16 here works is we say, hey, the depth of our root node is 0. Maybe I'll put it in purple here, 0. And then we're going to add this 0 plus recursive calls on this node and on this node, passing in a depth of 0 plus 1, because these two nodes have a depth that's 1 higher or 1 greater than this node. And so these depths would be 1. We would add these two values to this value, and then these two nodes would make themselves recursive calls to their children nodes with depths 1 plus 1, because all of these nodes here have a depth that's 1 greater than the depth of these two nodes. And so here you would get 2, 2, 2, 2. And then finally here, the recursive calls on these two nodes would get depths of 3. And so if you sum up 3 plus 3, 6, plus 2 plus 2 plus 2 plus 2, that's 8. 8 plus 6 is 14. Plus 1 plus 1, 16. Plus 0, 16. And we get that value that we had earlier. So let me undo again these values here and just very quickly write this recursive formula for calculating the sum of node depths for one particular binary tree. Not all of the subtrees, just one particular binary tree. So this is the answer to that easier question. Let's call it node depths. We'll write it out as ND for short. This method, ND, the recursive method, is going to take in a node and a depth, and it's going to be equal to the depth plus a call to ND on the left child node with a depth of D plus 1, plus a call to ND on the right child node with a depth of D plus 1. And so this is our recursive formula to get that 16, and this is the answer to that easier question that we have right here on AlgoExpert. Now, the reason that I'm going through this, the reason that I'm just reminding ourselves of this recursive formula here, is because there's a pretty obvious solution to this question, all kinds of node depths, which is if we know how to calculate the node depths for a particular subtree, like the tree rooted at 1, by just applying this formula, then all that we have to do to get the answer that we're looking for this question, the 26, is call this method, this node depths method, on every tree in this binary tree. So instead of just calling it on the tree rooted at 1, call it on the tree rooted at 1, and on the tree rooted at 2, and on the one rooted at 3, and on all of the others. So when we call it on the tree rooted at 1, we would get 16. This is what we wrote earlier, 16. Then we would call it on the tree rooted at 2, and we would get 6. Then on the tree rooted at 3, we would get 2. Then here we would get 2. And then on all the others, we would get 0. And then we add up all these values, and we'd get the answer. We would get 26. So here we've actually come up with a solution. The solution to this question is to iterate through every node in the binary tree, iterate through all of them, and we can do so either iteratively or recursively pretty easily. And at every single node, treat that node as the root of a subtree in the input binary tree, and call this node depths method that we have from that other question here on AlgoExpert, this recursive formula, call this method on all of these nodes. And that gives us all of these values, then you sum them up, and you get the answer 26. But is that a good solution? Well, let's look at the complexity analysis. We know that this node depths method here is going to take O of n time, because this method here traverses through all of the nodes in the tree that you call it on, that you originally call it on. Like if you call node depths on the tree rooted at 1, you're going to traverse through every single node in the tree rooted at 1. So this method here runs in O of n time. And the space complexity of this method is O of h, where h is the height of the binary tree that it's called on, and that's because of the recursive calls on the call stack. The space complexity isn't going to matter too much, but the time complexity, this O of n here, let me add time complexity. This O of n does matter, because with the current approach that we just went through, we are traversing through every single node in the binary tree, and then on each of those nodes, we're calling this method that's got an O of n time complexity. And of course, since we're traversing through every single node in the binary tree, that means that we're calling this method, this node depths method, n times. So we're doing this time complexity here n times. Now the good news is that when we do call this node depths method, this n refers to the number of nodes in the tree that we're calling the method on. And so with our approach, we're not actually calling this method n times on the root node. If we were calling it n times on the root node, then we would really be doing n O of n time complexity operations. Here, we're calling it on all of the nodes in the binary tree, which means that this O of n time complexity is actually going to be O of however many nodes there are in each subtree in the binary tree. And if we're dealing with a perfectly balanced binary tree, then this is going to be a total of, let's write it down up here, it's going to be a O of n log n algorithm. And the reason it's log of n is because at every binary tree that we call this node depths method on, we're effectively eliminating half of the nodes in the binary tree. And of course, if our overall binary tree isn't balanced, if it's skewed, then this time complexity starts to look a lot more like O of n squared. So I'll write it down just so that we have that in mind. Our algorithm, this approach that we just described of traversing through every single node in our binary tree, and at each node calling this recursive method here, this algorithm is going to run at best in n log n time, and at worst in n squared time. And then for the space complexity, we're likely going to be able to get away with a space complexity that's equal to the space complexity of this method, just O of h, where h is the height of the binary tree, and that'll be clear in the code. We're going to be able to implement this recursively or iteratively, and we're not really going to be storing extra stuff except for the stack that we use to traverse the binary tree iteratively, or the recursive calls on the call stack. So all that to say that the space complexity is going to be O of h, where h is the height of the binary tree. And as you can probably tell, the space complexity likely isn't going to be the issue or the thing to optimize for this question. The time complexity, however, is going to be the thing to optimize. Can we do better than this n log n algorithm or this n squared algorithm in the worst case? And of course, by asking ourselves if we can do better than n log n, what we're really implying is, can we solve this problem in linear time? Can we solve this problem by basically just doing a single pass through this entire binary tree, or maybe a couple of passes, even multiple passes, but not doing a bunch of traversals for each node, just singular passes through the entire binary tree? Is that possible? And what this question really entails is, can we find some sort of relation between this value, the node depths at a given node, like the 16 here, and these two values, the node depths of the children nodes of the node that we're looking at? Because here, The reason that we used this recursive method on every node was precisely because it doesn't look like there's a relation between this 16 here and this 6 and this 2. Because the depths of all of these nodes here, for example, the nodes in the subtree rooted at 2, the depths of these nodes relative to this 2 are different than their depths relative to this 1 up here. And so that's why we called this method on all of these nodes, not only because it just made sense, like we said, just get the node depths at every node and sum them up, but on top of that, there was no obvious way to get the values that we're looking for, like this 16, from these values that we may have computed in our algorithm. Now, if there were some relation between this value, like the node depths at a particular node, and the node depths at the children nodes of that node, then maybe we would be able to forego calling this node depths method on every single node and just apply whatever this relation would be to get this value, or even this value, the 6, from the 2 and the 0 here in constant time. So I'm going to erase everything that we've written out here to give us some space, and let's see if we can figure out if there is such a relation after all. It doesn't seem obvious at first. Let me move this here and erase it. It certainly doesn't seem obvious that there would be a relation, because this 16 here, what is it? 6 plus 2 multiplied by 2. 6 plus 2 is 8, and multiply 8 by 2 and you get 16, but that just seems weird. Like 2 plus 0 multiplied by 2 clearly isn't equal to 6. So to figure this out, let's try to take a step back and remind ourselves of what a node depth is. A node depth is the distance of a node to the root node of the binary tree that we're looking at. So if we take the binary tree that's rooted at 1, the depth of the node with value 2 is 1, because it's one level lower than the root node with value 1. The depth of the nodes 4 and 5 is 2, because these nodes are 2 levels lower than 1. And then the depths of the nodes with values 8 and 9 is 3, because they're 3 levels lower than 1. Now, if we look at the binary tree rooted at 2, the depth of the node with value 2 relative to the binary tree rooted at 2 is 0. The depth of the node with value 2 relative to the binary tree rooted at 1 was 1, because 2 was one level lower than 1. But the depth of the node with value 2 relative to the binary tree rooted at 2 is 0, because 2 is at the same level. So basically, if we're looking at the binary tree that's rooted at 1 and the binary tree that's rooted at 2, the depth of the node with value 2 relative to these two binary trees differs by 1. It gets incremented by 1 if we look at the binary tree rooted at 1. Now, what about these other nodes, like 4 and 5 and 8 and 9? Well, 4 and 5 relative to 1 have a depth of 2. But relative to 2, they've got a depth of 1, because 2 is one level deeper than 1. So relative to 2, it's only 1, but relative to 1, it's 2. It's a little bit confusing here because of the values, but you get the idea. We're one level deeper, so relative to this level, it's one level less to traverse, so the depth becomes one value less than the depth that they have relative to the upper level. And then if you look at the final nodes here, the leaf nodes, 8 and 9, it's the same thing. 8 and 9 have a depth of 2 relative to the node with value 2, but they've got a depth of 3 relative to the root node with value 1. So basically, every single node in this subtree here, the left subtree of 1, has a depth relative to this 1 that's 1 greater than their depth relative to this 2. So if you grab the depths of all of these nodes, 2, 4, 5, 9, and 8, if you grab their depths relative to 2, and then you add 1 to all of these depths, you get their depths relative to the node with value 1. But now if we go back to the problem at hand, because now we're going a little bit on a tangent, if we look at 16, 6, and 2 here, what was 6? 6 was the sum of the depths of all the nodes in the subtree rooted at 2. Because 4 and 5 had a depth of 1 relative to 2, 8 and 9 had a depth of 2 relative to 2, and 2 had a depth of 0 relative to itself. And so 2 plus 2 plus 1 plus 1 was equal to 6. But we just said that all of these depths, 2 plus 2 plus 1 plus 1 plus 0, all of these depths are 1 lesser than the equivalent depths of these nodes relative to the node with value 1 that's 1 level above the 2. So here, to get this 6, let me write it down here. To get this 6, we did 2 plus 2 plus 1 plus 1 plus 0. These were all of the depths of these 5 nodes relative to the node with value 2. But now the depths of all these nodes relative to the node with value 1 is all of these depths plus 1 on each of them. So suddenly it's 3 plus 3 plus 2 plus 2 plus 1. These values here, which are just these values incremented by 1, represent the depths of all of these nodes relative to the node with value 1. And the same thing applies here, by the way. Like here for the tree rooted at 3, we had a 2. Let me write it down here. 2 was equal to 1 plus 1 plus 0, because the depths of the nodes with values 6 and 7 was 1, and the depth of the node with value 3 was 0, if we're talking relative to 3 here. So it was 1 plus 1 plus 0. But then if we wanted to get the depths of these 3 nodes, this time relative to the node with value 1, we would just increment all 3 of these values by 1. So suddenly you would get 2 plus 2 plus 1. And here now, if we add all of these green values here, you actually get the 16, right? 3 plus 3 is 6, plus 2 is 10, plus 1, 11, plus 1, 12, and then plus 4 is 16. So, okay, that's great, but here what we've essentially done is just rewritten our recursive formula just a little bit differently. Like in the recursive formula, you call the recursive function on every node and you pass a depth of d plus 1. Here, that's effectively what we did by just incrementing all of these values by 1. And of course, we have n values here, so this doesn't really help us. It doesn't really bring us anywhere. Unless we realize that here, incrementing all of these values by 1 is the same thing as grabbing this sum here, 6 or the 2, and adding the total number of nodes in the tree that's rooted at the node that this 6 was obtained from, or that this 2 was obtained from. In other words, here, 3 plus 3 plus 2 plus 2 plus 1, this was obtained by adding 1 to all of these values, or what we could have done 2 plus 2 plus 1 plus 1 plus 0, plus the total number of nodes in the tree that was rooted wherever we got the 6, which is here, the tree rooted at 2. How many nodes were in this tree? 1, 2, 3, 4, 5. So plus 5 here. Because basically what we're saying is there are 5 nodes in this subtree here. We know that the node depths of all these nodes in this subtree rooted at 2, if you add them up, they give you 6. We know that their depths should be 1 higher if we're looking at the tree that's 1 level higher than the tree rooted at 2. So if we wanted to obtain all of the depths of these nodes relative to the root node here, or the node 1 level higher, we would have to increment them all by 1, or incrementing them all by 1 is equivalent to just adding the total number of nodes. There are 5 nodes. If you're incrementing 5 depths by 1, it's the same thing as just adding 5. Adding the number of nodes in the subtree. Okay, so let's try to actually grasp what it is that we've done here. So let me erase all of this. I'll erase all of this here, and let's move our binary tree to give ourselves some space. We said that this 16 here, which was equal to the node depths, the return value of that recursive method that we had written. I'll write it down, ND, except this time, instead of writing our recursive formula, I'm going to compute ND using the logic that we described down here with the numbers that we had written down here. So what was ND? It was equal to NDL. I'll call NDL the node depths of the left subtree, which was 6. Maybe I should put an arrow. Wait, let me give myself a little bit more space. We'll put the arrow above. So in green, this here is 6. This here is 16. So NDL plus the number of nodes in the left subtree, and that's equivalent to adding 1 or incrementing by 1 all of the individual depths that led us to this 6 right here. But so plus the total number of nodes in the left subtree. So I'll write, maybe we'll put a hashtag for the number of nodes, number L. And this here is equal to 5 in our case, because we've got 1, 2, 3, 4, 5 nodes. And then plus NDR plus number of nodes in the right subtree. And NDR is going to be equal to 2. So this 2 right here. And the number of nodes in the right subtree is going to be 3, because here we've got 1, 2, 3 nodes. And now if we add up 6 plus 5 equals 11, plus 2, 13, plus 3, and we've got this 16. Now, of course, at this point, you might be wondering, well, wait a second, is this actually even useful? Like, why are we doing this again? Well, it is useful because now that we have this formula, we can use it to compute all of these node depths. Like, not just the 16, but also the 6, also the 2, also this 2, and also all of these zeros. And these are probably going to be some sort of base case. Now, of course, we have to make sure that this is actually better than our previous algorithm. Can we do this in linear time? Or is this also going to involve having to do, log of n or n computations for all n nodes? Well, let's see. ND depends on NDL, NDR, and number L and number R. So we can basically cross one of these out, because if we figure out how to compute these two things, then these two things will follow. These two lines here are basically equivalent. So here, NDL and number L. Well, NDL, we can just apply this formula to compute NDL. Like if NDL here is 6, which is the value relevant to this binary tree here, to get this 6, we can just say ND equals NDL, which would be on this 4, plus number L on this subtree rooted at 4, and then NDR and number R on the subtree rooted at 5. So the NDL here isn't the issue, because NDL will follow the same formula as ND. The question is, can we get number L, the number of nodes in a subtree, fast? Like, is this going to be an expensive operation? And here the answer is no. It's not going to be an expensive operation because you can just do a single pass through a binary tree and compute the number of nodes in every subtree. Computing the number of nodes in every subtree in a binary tree is a pretty trivial task. You just have to traverse it, and you can either store the number of nodes in a subtree on the nodes themselves if you mutate them, or you can store them in a hash table of some sort. But the point is, this number of nodes in a binary tree isn't difficult to get. It's pretty trivial to compute that. And that is the key to this formula here and to this overall algorithm. This is what's going to allow us to solve this question in linear time. Now here, I don't want to spend too much more time on the conceptual overview because I think that things will get a lot more clear when we just look at the code and actually implement this out. but I will just walk through one time this entire example following this formula, just so that we can all be convinced that this actually works and is going to run in linear time. So let me erase this for a second here. We'll erase this and we'll move our formula. You'll have to forgive the fact that it's crossed out at the bottom here, but let's move it up here. And let me grab our binary tree and put it in the middle here. We're going to erase all of these ND values. All of these green values here were these ND values, the node depths, but we're going to compute them really quickly by walking through this example. Now again, things are going to be a lot clearer in the code, but basically, the way that we're going to implement this algorithm is we're going to start at the root node, and we're going to traverse the tree. We're probably going to go all the way to the bottom. At the bottom, we've got base cases where we know that the number of nodes in these subtrees, the trees rooted at the leaf nodes, the number of nodes in those subtrees is 1. So I'll write, maybe in brown, the number of nodes in each subtree. So here, this is going to be 1, 1, 1, 1, 1. And then I'll write in green the actual node depths of all of these nodes. So the node depths of leaf nodes is going to be 0. That's also going to be some sort of base case. And the reason it's going to be 0 is if you apply our formula here, this formula, ND equals NDL plus number L plus NDR plus number R, none of these leaf nodes have any left subtrees or right subtrees. So there's nothing to add, hence 0. However, these subtrees rooted at these leaf nodes have one value or one node each. So basically, to get all of these values here, the 0, 1s for all of these leaf nodes, took constant time. For each of them, it took constant time. We knew, because we were at a leaf node, we knew that it was 0, 1. Now let's go to this 4. This 4 here, let's apply our formula. ND, what's the node depth of this tree here, the tree rooted at 4? Well, it's NDL, node depths of the left subtree, which is 0, plus number of nodes in the left subtree, which is 1. We've stored these values somewhere, either on the node or in some sort of hash table, or maybe we've implemented this algorithm in such a way that we return these values. You'll see this in the code. Point is, we have these values somewhere. So 0 plus 1 plus NDR, which is 0, plus number R, which is 1. So 0 plus 1 plus 0 plus 1, 2. So we now have 2. And for the total number of nodes in this subtree, it's the total number of nodes in the left subtree plus the total number of nodes in the right subtree plus 1, because we've got one more node here. So 1 plus 1 plus 1, that's 3. Now we move on to the tree rooted at 2. So ND, node depths for the tree rooted at 2. Remember, ND here I think was equal to 6. We had a 6 here for the 2. But let's apply our formula. NDL, the node depths in the left subtree, is equal to 2, plus the number of nodes in the left subtree, which is equal to 3, plus NDR, 0, plus number R, 1. So 2 plus 3 plus 0 plus 1, that's equal to 6. And then for the total number of nodes in this subtree, just add the total number of nodes in the left subtree, so 3, plus the total number of nodes in the right subtree, so 1, 3 plus 1, plus 1, because we've got one node here. So that's 3 plus 1 plus 1, 5. We've got 5 here. Then we do the same thing for the 3. ND for the 3 is going to be equal to NDL, 0, plus number L, 1, plus NDR, 0, plus number R, 1. That's 0 plus 1 plus 0 plus 1. That is 2. Number of nodes in this subtree, 3. And finally, for the binary tree rooted at 1, ND is going to be equal to NDL 6 plus number L 5 plus NDR 2 plus number R 3. And that's equal to 6 plus 5, 11, plus 2, 13, plus 3, 16. So 16, for the sake of good order, we're going to also put the total number of nodes in this subtree. So that's going to be 5 plus 3 plus 1. So 9. So there are 9 nodes in our total binary tree. And then finally, to get the 26, we just retraverse through the entire tree. Or again, if we've been returning all of these values through our algorithm. We'll see this in the code. Maybe we have the answer right then and there. But the point is we can just traverse through this entire tree, get all of these green values, add them up, and we get 26. 16 plus 6 is 22, plus 2, 24, plus 2, 26. And so hopefully at this point, you understand why the time complexity of this algorithm is just going to be O of n, so linear time complexity, where n is the total number of nodes in the binary tree. And the reason it's O of n is because we are traversing through every node in the binary tree, and there are n nodes. But at every node, all that we're doing is applying this formula, and applying this formula is a constant time operation. And we can build up all of these values, all of these green and brown values in constant time by applying this formula. And it all starts at the very bottom, at the leaf nodes, where we get these values, these zeros and ones, for free. Now, as I've hinted multiple times throughout this example, we're going to be able to implement this in a couple of different ways. One way is going to have us do multiple passes through this binary tree. So we'll be doing, a traversal through n nodes to compute, let's say, all of the brown values, then another traversal through all of the n nodes to compute the green values, and then finally a third one to compute the final answer. For that particular implementation, we'll still have an O of n time complexity, but we'll also have an O of n space complexity. So I'll write it space equals O of n. And the reason it'll be O of n for that implementation is because we'll actually be storing all of these values. So we'll be storing n extra values, or even 2n extra values. But as you'll see in the code walkthrough, there's actually going to be a way to implement this solution without storing all of these values, just by having one single recursive method return all of these values at every iteration and using them to build our final answer. And so with that implementation, we're not going to have to store n extra values, and so we'll just have the recursive calls on the call stack that are going to be taking up auxiliary space. And so for that solution, it'll actually be O of h, at least when the binary tree is balanced, where h is the height of the binary tree. With that, let's dive into the code walkthrough to see what this looks like. All right, so we've got our all kinds of node depths function defined. It takes in the root of a binary tree, and you'll notice that I've already written out this method, which is our recursive node depths method. This is actually the solution to that easier question that we've got right here on AlgoExpert, and we're going to use it for two of our solutions here. It's a very simple recursive method, takes in a node and the depth of a node that defaults to 0. If we are at the none value or the null value, then the depth is 0. Otherwise, we sum the depth plus two recursive calls of this method on the left node and the right node, and we increment the depth that we pass to these two recursive calls. So I'm going to start out by implementing two versions of the naive solution, where we iterate through the entire tree, and at every node we call this recursive method. I'm going to do one implementation that does this iteratively, and one implementation that does this recursively. These are going to be our two naive solutions, so to speak. And then we'll get into the optimal solutions. We're also going to be doing two that implement that second thing that we covered in the conceptual overview, the thing with the new formula, the new node depths formula. So let's start with these two naive solutions. We'll start with the iterative one. So we're going to have the sum of all of our depths, sum of all depths, that starts out as 0. And for the iterative solution, we want to traverse through the entire tree iteratively. So we're going to use a stack. Our stack is going to start out with just our root node. And so long as our stack is non-empty, so long as it's got a length that's greater than 0, we're going to pop off the stack the next node that we want to iterate through. So this node here. And we're going to say if the node is none, then we just continue. Otherwise, the sum of all the depths is equal to, or we increment it by a call to this recursive method, node depths on the given node. And then we add to our stack.append node.left and node.right, and we're done. We eventually return the sum of all the depths. So as you can see, this solution just traverses through every node in the binary tree, starting at the root node, and for every node, we add to this running sum the return value of this recursive method on that node. And so this while loop here is going to take O of n time, because we're traversing through n nodes. And then at every node, we're calling this recursive function that takes O of n time, where n is the total number of nodes in the binary tree that's rooted at the node that we pass here. And so if our tree is balanced, all of these binary trees are going to have half of the remaining nodes in the binary tree in them. So they're going to be smaller and smaller and smaller, cut down by half. So this is going to be an O of n log n algorithm in time complexity. And then the space complexity is going to be O of h, and this is going to be because of the stack. And we covered this in that easier question that we have here on AlgoExpert. Now we can do the same exact thing for the second version of this naive solution, which is going to be the recursive version. So I'll just duplicate this. I'll comment this out. And by the way, here, if the tree weren't balanced, then this would be n squared, because you might have basically a completely skewed linked list like tree. And in that case, these node depths calls would really act like an O of n algorithm, where it would kind of imitate a double for loop, so to speak. But so the recursive version of this is going to be really simple. It's going to be basically as simple as this recursive method. We have to handle the base case where the root is none. So if root is none, then return 0. Otherwise, what is our recursive formula? Well, it's all kinds of node depths on root.left plus all kinds of node depths on root.right. So it's very similar to this method here, except we make a call to node depths on the root. So we're using this recursive method here on every node, right? On every node that we call our main method with. And then for all of these nodes, we also call this main method on their left node and on their right node. And so in all of these recursive calls, we're going to repeatedly call node depths on each node. And we're basically doing the exact same thing that we do up here in the iterative version. So this is also going to run in O of n log n time and O of h space. And again, this is when the tree is balanced. And by the way, h is the same thing as log of n when the tree is balanced. I suppose the h makes a lot of sense when you're talking about the recursive calls on the call stack, because you can actually count them. But that is what the time and space complexity is for this solution. So these were the two naive solutions, or the two bad solutions. Now let's cover the two good solutions that are going to use our second formula. And both of these solutions are going to run in linear time. One of them is going to actually store those values that we wrote in green and brown in the conceptual overview. It's actually going to store these values and do multiple passes through the binary tree, eventually using the green values, summing them up, and getting the final answer. The second implementation is going to bypass all of that and just find the answer in a single pass through the tree. And it'll be just a little bit more nuanced, maybe, as far as how we implement our recursive function. But so this is the first version, the version where we do store those values. And so for this version, we're going to do 3 passes through the entire tree. During the first pass, we're going to store or calculate and store the total number of nodes in every subtree in the tree. Then during the second pass, we're going to calculate all of the node depths of every subtree using the formula that relies on the total number of nodes in subtrees. And then finally, we're going to do one third pass where we sum up all of the node depths and we get the final answer. So, depending on your language and depending on how you want to implement this, you've got a couple of options. One option is to actually mutate the nodes in the tree. If you were writing this in JavaScript, I would probably recommend that you do that just because it's very easy to mutate classes or instances of classes in JavaScript. Here in Python, I'm just going to store the counts and the depths or sum of depths in hash tables. So I'm going to have a node counts, which is going to be equal to a hash table or a dictionary. And I'm going to have a node depths, which is also going to be equal to a hash table or a dictionary. And then I'm going to have two helper methods. These are going to be, and let me give myself a little bit of space here. These are going to be our two first passes through the tree. So add node counts, and it's going to take in the root and the node counts. And then here add node depths, and this is going to take in the root, the node depths. And we're also going to need to rely on the node counts here because to calculate the node depths, we apply our formula, which uses the counts. And the counts here, this is how many nodes are in every subtree. And then finally, we're going to return, and here we're going to have another helper method, which we'll call sum all node depths. And this is going to do one more traversal and add up all of the node depths. So this is going to take in the root and the node depths dictionary. So here, perhaps the most logical way of writing this out is to start with this method, the node counts method, then the add node depths method, and then this one. So we'll go with add node counts. It takes in a root, or let's just call this a node, and it takes in node counts. And here, we're really just counting the number of nodes in a binary tree. So that means taking ourselves, the current node that we're at, and adding whatever we've found in the left subtree and in the right subtree. And we're eventually going to reach a base case. So here we'll do something like node counts of node, right? We're storing the node as the key in our hash table. In Python, you can do that. And here, you could have an ID if you wanted to, whatever you want. I'm just going to use the node as the key. So node counts of node is going to be equal to 1. And if node.left is not none, then I want to do stuff. If it is none, then I don't have a left subtree. And here, similarly, I'll say if node, let me pass up here, if node.right is not none, then I'm going to do something. Otherwise, I pass. So what this does is it means that if I don't have a left subtree, like if I have none as my left node, and if I have none as my right node, then I don't do anything here. And I've just set the node counts at the tree rooted at my node, which is a leaf node, not a root node, a leaf node, to 1. And that would be correct. That would be what we want. If you remember, the base case in the conceptual overview, the base case for the brown values was 1. At the very bottom, the leaf nodes have a single node in the subtrees rooted at themselves. Now, if we do have a left node or a right node, then what we're going to do is we're going to make a recursive call to this node counts method, or add node counts method. And we're going to make the recursive call to node.left, passing in node counts. And then we're going to say, let me delete this, we're going to say node counts of ourselves plus equal to node counts of node.left. Node.left. Whatever we have computed through this call, right? We're making this call, which effectively mutates this dictionary or this hash table, and whatever we've stored in node.left, node counts at node.left, we want to add to our node counts at our current node. And then we're going to do the exact same thing here for the right node, except we'll pass in right, and here right. So this is a very simple way of just counting the total number of nodes in every single subtree in linear time. Because if you look at this, we're traversing through every single node in the binary tree, and at every single node, we're just doing constant time operations, because these recursive calls here, these are basically traversing through the n nodes. So this allows us to calculate and store the total number of nodes in every subtree in linear time. And now we're going to use these newfound node counts to calculate the node depths. This method, add node depths, is actually going to look very similar to this one, except it takes in node depths here on top of the node counts. And we're going to do the same thing, except our base case is 0, not 1. If you remember, at the very bottom, if we're a leaf node, we've got a node depth of 0. And then, if we don't have a left node, and if we don't have a right node, then we're just going to do nothing. We're going to keep this as 0 here. But if we do have a left node, or if we do have a right node, we're going to make calls to add node depths. We're going to make recursive calls to the left and right nodes. And here, I should pass in node depths to both of these calls. And then here we're going to calculate. So let me do this one at a time maybe. This is going to be node depths at our current node plus equal to, and we apply our formula. So what was our formula? ND equals NDL plus number L plus NDR plus number R. So here we're dealing with the left node, so it's equal to node depths that we've calculated at node.left. We just calculated it here with this recursive call, plus node counts of node.left. And this thing here is basically equivalent to grabbing all of the depths of the nodes in the left subtree, all of their depths relative to the left subtree node to node.left, and incrementing all of their depths by 1. That's what we covered in the conceptual overview. And this allows us to calculate the node depths. This allows us to do this recursive method, where is it? This recursive method here, which by the way, I should move this because I don't need it anymore. This allows us to do that method, which I'll comment out, in constant time with this nice little formula. And then we can apply the same exact thing here for the right subtree, except it'll be right. And to reiterate one last time, this method here is going to traverse through every single node. So we're going to traverse through n nodes, but at every node, we're just doing constant time operations. So we're calculating all of these node depths that clearly took a while up here with this recursive method. If we had to do this one n times, here we calculated all of these values and stored them in our node depths here in linear time. And then finally, we can write out our main method here. And this one is just going to take in a node and node depths. And this one is going to be pretty easy. If the node is none, then we return 0. Otherwise, it follows kind of the same structure as this, right? We return sum all node depths, node.left, pass in node depths, plus sum all node depths, node.right, pass in node depths, plus node depths of the node. And here, this is key. Like basically, this method here is identical to this one, except instead of doing this recursive call here, we are doing this constant time check in this pre-computed dictionary or hash table. And so this is just yet another linear time method here. So we've got 3 linear time methods. And so this means that our algorithm runs in linear time. And then for the space complexity, it is going to be O of n space. So it's no longer going to rely on the height because, as you can see, we're storing in these 2 hash tables n values. Right? We're storing the n counts and we're storing the n node depths. And then at the very end, we use them to find our final answer. So that gives us O of n space here. So now we've got one last version to implement. It's going to be an optimal version. So same overarching logic as what we just implemented here, except instead of storing all of the values in our node counts and node depths here, we're just going to have one recursive method return all of the necessary info at every iteration. So let me comment this out. And by the way, the reason that you might want to do that is because, first of all, it'll lead to a better space complexity. We just won't have to store, n extra things. And depending on the type of person you are, it might speak to you a little bit more. You might understand this logic a little bit more than this logic. Even though, to be honest, this one is probably easier to reason about because you go step by step. First you calculate the counts, then the depths, and then you sum all of them. Whereas here we're going to do everything all at once. But for some people, that's just the kind of solution that they would come up with, more so than this particular solution here. And if you're not one of those people, then maybe this is just a good example of how you could implement this differently. But so let's write it out down here. I'll give myself some more space. We're going to have our main method. So def all kinds of node depths. It takes in the root. And here, like I said, we're going to have one main recursive method that returns all of the necessary information at every iteration. So we're going to return basically node counts. We're going to return node depths. And we're going to return the running sum at every call to this recursive function. So I'm actually going to call this recursive function, I'll pass here for now. I'm going to call this recursive function getTreeInfo because we're going to be carrying a lot of information as we go through it. So this is going to take in a tree. And here, I'm probably going to use a class. I could use a dictionary for this. I'm going to use a class just so that in Python I don't have to write strings like this to access keys off of a dictionary. So let me pass here. But so we're going to have a class called TreeInfo, and this class is going to take in number of nodes in the tree. It's going to take in the sum of depths. This is going to be equivalent to the node depths. And number of nodes in the tree is going to be equivalent to the node counts. And it's going to take in the sum of all the depths. And this is going to be our running sum. And it'll store these things. So num nodes, and here like this. And so this is the structure that we're going to be returning at every step of this function or every step of this solution. So here in this recursive call, we're going to say if the tree is none, this is our base case, then we return, what do we return? Well, TreeInfo, because we return, an instance of this class. If we are at the very bottom of the tree, not even the leaf node, or at the bottom at a none value or a null value, we don't have any nodes in the tree, so this is going to be 0. We don't have a sum of depths, so this is going to be 0. And we certainly don't have a running sum, so this is also going to be 0. Now, in the spirit of making this very clear, I'm going to try to write this out step by step. So first, we're going to get the tree info of our left subtree, and then the tree info of our right subtree. So left tree info equals, I make a call to this recursive method, tree.left, then right tree info, and I make a call to tree.right with the recursive method. So now we've made the calls to this recursive method on all of the nodes. Like just this alone here traverses the entire tree. Now, of course, we need a little bit more logic. We need the meat of our logic now. So we know that this method has to return a tree info. So here I can just already do return tree info, and this will take in num nodes in tree. We're going to calculate this, sum of depths and sum of all depths. Now, the question becomes, how do we get these three values? Num nodes in tree should be pretty easy. It should be equal to 1, because there's the current node, right? That's one node, plus left tree info dot num nodes in tree plus right tree info dot num nodes in tree. Now, for the sum of depths, this is where we're going to need our formula. Sum of depths is equal to NDL plus number L plus NDR plus number R. So let's actually calculate these above here. Sum of left depths, so this is like the top row, NDL plus number L from the conceptual overview. This is going to be our formula, left tree info dot sum of depths. Sum of depths. This is NDL. This was 6 in our example when we were looking at the subtree rooted at 2, plus left tree info dot num nodes in tree. And then for sum of right depths, it's the same thing. We mirror it. So here we take the sum of depths in the right tree and the number of nodes in the right tree. And these two pluses here are equivalent to incrementing all of the individual depths by 1 of all of the nodes in these subtrees. And so here sum of depths now is going to be equal to this plus sum of right depths. And this is adding up these two values here is equivalent to adding up these 4 values, right? These 4 values here. And that is exactly our formula that we wrote in the conceptual overview. And it's similar to what we just did here, except here, we had preemptively, here it was this step. We had preemptively calculated the node counts, and we added to our node depths at a particular node this, which was equivalent to this. And then we did the same thing in the right subtree, which was equivalent to this. And so now finally we have the sum of all the depths, and this is equal to, well, it's equal to the sum of depths for our current node, right? That would be 16 in our root node in the conceptual overview, plus left tree info dot sum of all depths, plus left or right tree info dot sum of all depths. And here it's very important that we pass these running sums, because remember, like in the conceptual overview, we had 16 at the root node, the sum of depths, plus 6 plus 2. 6 was in the left subtree and 2 was in the right subtree. But then there was another 2 in the left subtree. Like if you went all the way down to the subtree rooted at 4, there was another 2, because those were the node depths at that subtree. This 2 isn't reflected in left tree info dot sum of depths. It is reflected in left tree info dot sum of all depths. So this is very important here. And that is the final step in this algorithm. And then we create our tree info with these values that we just calculated, and we are done. At the very top here where we passed, we just return get tree info, we pass in the root, and we grab sum of all depths. And now we get the sum of all depths at the root, because this is going to return this tree info for the root node, and we are done. And this is going to run in O of n time, and O of H space when the tree is balanced. Because here, as you can see, we're not storing, like at any given point in time, all that we have is a singular tree info, right? And then we have, all the recursive calls on the call stack, but that's it. We're not storing n counts, we're not storing n depths all at the same time. And so that's why we have a slightly better space complexity. And putting aside the space complexity, because in an interview, this would be a perfectly fine solution. Like, you would not be penalized for having implemented this solution versus this one. But this is just a good example of how you could solve this question a little bit differently. Right? One way involves precomputation and multiple passes through the tree. The other way doesn't involve precomputation, does everything in a single pass, and it's still pretty readable. You can still write this code out in a way that you understand what's going on. But so that's it for this question. This is all kinds of node depths. This is definitely a tricky question that's got a lot of stuff going on, a couple of different ways of implementing this solution. And with that, I hope that you found this video informative, and I'll see you in the next one.